In this video, we learn about the solution of numerical algebraic and transcendental equations. So before going to see about the finding the solution, we see some introduction part. That is, in the field of science and engineering, the solution of equations of the form f of x equal to 0 occurred in many applications. F of x is a polynomial of degree 2 or 3 or 4, exact formulae are available. But if f of x is transcendental function like a plus b e power x plus c sin x plus d log x, etc., then the solution is not exact and we do not have a formula to get the solutions. When the coefficients are numerical values, we can adopt various numerical approximate methods to solve such algebraic and transcendental equations. We will see below some methods of solving such numerical equations. Also, from the theory of equations, we recall one theorem, that is, if f of x is continuous in the interval open interval a comma b, and if f of a and f of b are of opposite sign, then the equation f of x equal to 0 will have at least one real root between a and b. So by using this concept, we see some methods of solving such numerical equations. The first method is the bisection method or Boltzmann's method or interval halving method. Suppose we have an equation of the form f of x equal to 0 whose solution is in the range open interval a comma b is to be searched. That is, this interval open interval a comma b can be obtained from the theorem. That is, if f of x is continuous in the interval a comma b, then f of a and f of b are of opposite sign, then f of x equal to 0 will have at least one real root between a and b. So by using that concept, we can choose the initial value. We assume that f of x is continuous, and if f of a and f of b are of opposite sign, then we choose the initial value x naught equal to a plus b by 2. Suppose this f of x naught sign is negative, then the root lies between a and x naught. Suppose f of x naught sign is positive, that is the value is positive value, then the root lies between x naught and b. So any one of this is true. Now we see that from the figure here, in the x-axis we take a and b value. So we assume that f of a is positive and f of b is negative. So the initial value x naught is the midpoint of a plus b divided by 2. So it is between a and b. Suppose if we have f of x naught is positive, then the root lies between x naught and b. So the root will be x1 equal to x naught plus b by 2. Now we find the sign of f of x1. Suppose f of x1 is negative, then the root lies between x naught and x1. So let the root as x2 equal to x naught plus x1 by 2. Now f of x2 is negative means then we have the root which lies between x naught and x2. So take the midpoint of that. So we have x3 equal to x naught plus x2 divided by 2 and so on. So in this way we continue the process. Then we obtain the sequence of approximate root x0, x1, x2, etc., whose limit converges to x exact root. That is, for example, if you get x11 and x12 are same, Then we stop the procedure and we can say that we have the exact root up to 4 or 5 decimal places. So this simple convergence method is slow but sure. So consider first example. Find the positive root of x cube minus x equal to 1 correct to 4 decimal places by bisection method. So here f of x equal to x cube minus x minus 1. So we first assume that the a value as 0. Then f of 0 equal to minus 1, which is negative, and f of 1 equal to negative value minus 1, and f of 2 is positive value. So we can say that f of 1 is negative and f of 2 is positive. So the root lies between a, 1 and 2. We can take the range as 1, 2 and proceed. So we take that x1, x0 as 1 plus 2 divided by 2, so which is 1.5. So f of 1.5 is 0.8750, which is positive. So we have the root lies between 1 and 1.5. So see that x0 is 1.25 and x1 is 1.25 plus 1.5 divided by 2, since f of 1.25 is negative. So continuing in this way, we will see that x6 as 1.3243 and x7 as 1.3263. So this root is correct up to 2 decimal places. In general, we consider 4 decimal places. So we can move on to the next iteration. So in continuing in this way, that is, we are going to see the positive and negative sign of f of x. Then we are shortening the interval, and we find that at x11 the value is 1.3247 and x12 as 1.32475. So we can tell that the approximate root is 1.3247 correct to 4 decimal places. So by using that bisection method, we obtained the root of the given f of x. The next method is the iteration method or method of successive approximations. Suppose we want to find the root of equation f of x equal to 0, we write f of x as x equal to I of x. Then we start with the initial approximate value x0 and actual root as alpha, and we write x equal to x0. So we have x1 equal to pi of x0. So continuing in this way, we have the successive approximations x2 equal to pi of x1, x3 equal to pi of x2, and etc. xn equal to pi of xn. If the sequence of approximate roots x1, x2, etc. xn converges, then and it approaches to alpha, that is, the approximate root approaches to alpha. So next we see about the condition of the convergence of the method, that is, if f of x equal to 0 be the given equation whose actual root is alpha, then the equation f of x equal to 0 be written as x equal to pi of x, and let I be the interval containing the root x equal to alpha. Then if pi dash of modulus of pi dash of x is strictly less than 1 for all x in I, then the sequence of approximations x0, x1, etc. xn will converges to alpha if the initial starting value x0 is chosen within I. So the condition for the convergence is modulus of pi dash of x is less than 1. Next we see the order of the convergence of an iterative process. Let x0, x1, etc., xn, etc. be the successive approximations of the root alpha of f of x equal to 0, and let ei be the error in the root xi. Then if alpha is the exact root, then ei equal to xi minus alpha and ei plus 1 equal to xi plus 1 minus alpha. If p greater than or equal to 1, then we find that modulus of ei plus 1 less than or equal to modulus of ei whole power p into k, where k is a positive constant and p is called the order of the convergence. If p equal to 1, then we can say the convergence is linear. If p equal to 2, then we can say that the convergence is quadratic. So we see one example related to this iteration method. Find the positive root of 3x minus root of 1 plus sin x equal to 0 by iteration method. So first we have to write the given equation as x equal to. Then we can make x equal to pi of x. And we choose x naught. So like that we have to proceed. So first write the given equation as 3x equal to root of 1 plus sin x, or x equal to 1 by 3 into root of 1 plus sin x. Now consider this as pi of x. Now we have to see the condition of convergence. So for that we have to differentiate this once. So we have pi dash of x equal to cos x divided by 6 into root of 1 plus sin x. Now modulus of pi dash of x is modulus of 1 by 6 into cos x divided by root of 1 plus sin x, which is less than 1 for all x, when the root lies between 0 and 1. So we assume that f of 0 and f of 1, and we see the sign of the f of 0 and f of 1. So we have we have the value of f of 0 is negative and f of 1 is positive. So we can choose that interval as open interval 0, 1. So in that open interval 0, 1, modulus of pi dash of x is less than 1 for all x. So we can use the iteration method. So take x naught as any value. Here we can choose x naught equal to 0.4, which is any point between 0 and 1. Then x1 equal to 0.39291 and x2 equal to 1 by 3 into root of sine of x1, root of 1 plus sine of x1, which is 0.39199, and x3 equal to 1 by 3 into root of 1 plus sine x2, which is 0.39187. So like that it goes. And for x4 and x5 we have the similar root up to 5 decimal places. So we stop the procedure and we can say that the root is 0.39185. So we see one more method, that is regular falsy method or method of false position. Consider the equation f of x equal to 0 and let f of a and f of b of opposite sign, and let a less than b. The curve y equal to f of x will meet x-axis at some point between a comma f of a and b comma f of b. That is, when we consider this figure, here we have the point a, that is a comma f of a, and a point b, b comma f of b. So f of a and f of b are opposite sign. So there is a curve between a and b, and we see that here it meets at x-axis. So this will be our exact root. So we have to obtain this exact root by approaching that through the shortening of intervals. So we will move on to the method. Also we know that the equation of chord joining 2 points A and B is y minus y1 divided by x minus x1 equal to x2 minus x1 divided by y2 minus y2 minus y1 divided by x2 minus x1. So here we substitute y1 as f of a and y2 as f of b, x1 as a and x2 as b. So we have the equation y minus f of a divided by x minus a equal to f of a minus f of b divided by a minus b. The x coordinates of the point of intersection of this chord will with the x-axis gives an approximate value for the root of f of x equal to 0. Now setting y equal to 0 in the chord equation, we have, suppose if we substitute y equal to 0 here, then we have minus f of a divided by x minus a equal to f of a minus f of b divided by a minus b. So we have the equation x1 equal to a into f of b minus b into f of a divided by f of b minus f of a. So this value of x1 gives an approximate value of the root of f of x equal to 0. That is, x1 lies between a and b. Now we see the sign of f of x1. Suppose f of x1 and f of a are of opposite sign, or f of x1 and f of b are of opposite sign, then we have x2. That is, if f of x1 and f of a is less than 0, then x2 lies between x1 and a. If f of x1 is greater than 0 and f of a is less than 0, then x2 lies between x1 and a. So we have x2 equal to a into f of x1 minus x1 into f of a divided by f of x1 minus f of a. In the same way, we get x3, x4 and so on. This sequence x1, x2, x3 will converge to the required root. So we have that the exact root. So we see the example, solve the positive root of x minus cos x equal to 0 by regular falsy method. So we have f of x equal to x minus cos x. So first we see the interval of convergence. For that, let f of 0 which is negative, f of 1 which is positive. So we have the root lies between 0 and 1. So in the formula we substitute instead of a and b 0 and 1. So we have x1 which is 0.685078. Now we see the sign of f of x1 which is negative. So we have the root lies between x1 and 1. Similarly, we find x2. Then we see the sign of f of x2. So here f of x2 is negative. So we have the root lies between 0.736299 and 1. Similarly, in x3, we have f of x3 and it is negative value. So the root lies between 0.738945 and 1. So continuing in this way, we have x4 which is also 0.739191. So we can stop the procedure and we can say that it is correct to 4 decimal places or 3 decimal places. The value is 0.739 correct to 3 decimal places. So these are all the methods which are used to solve the algebraic and transcendental equations, and these methods are very useful for finding the roots of the given equation. Thank you all.